What happens when a massive star dies? Does it always collapse into a black hole, or could it become something stranger? Physicists have proposed the gravastar, an object that wears the mask of a black hole but hides a radically different interior. No singularity, no event horizon. Instead, a hollow bubble filled with vacuum energy, stabilized by a shell of exotic matter. To distant telescopes, it would be indistinguishable from a black hole. But if gravastars exist, they may hold the answers to some of science's greatest puzzles, from the information paradox to the fate of collapsing stars. In this documentary, we'll follow the story of gravastars, their theoretical birth, the physics behind them, and the ongoing hunt to distinguish them from black holes. Are gravastars the universe's hidden truth, or just a daring illusion? If you love unraveling cosmic mysteries, subscribe and explore more of our space documentaries, because what we see in the sky is never the whole story. Black holes have always been the monsters of the universe's tales. Not mythical beasts, not demons from ancient scriptures, but real, physical nightmares written into the very fabric of space-time. They do not roar, they do not move with claws or wings, they simply wait. Dark, bottomless pits, invisible, yet inescapable. They crush stars into dust, twist time into loops, and swallow entire worlds without a sound. For decades, they have ruled the cosmic imagination as the final word on destruction. But here's the question: what if black holes aren't the ultimate story of extreme gravity? What if the universe has been hiding something else, something stranger, in plain sight? A shadow masquerading as a shadow. An object that wears the mask of a black hole, but is not one at all. That object is the gravastar. Imagine standing on the surface of a dead world, its sky fractured by the glow of a nearby supermassive black hole. You'd see stars pulled into spirals, their light bending and stretching as though reality itself were being twisted through a cosmic lens. To most of us, this would be the ultimate horror, the universe revealing its dark, merciless side. And yet, physicists whisper of something even more unsettling. A gravastar would look identical to that monstrous hole in the sky, its pull on matter just as ruthless, its silhouette just as consuming. But inside, there is no singularity, no infinite point where physics collapses. Instead, there is something else, something pulsing, a hollow heart filled with vacuum energy, wrapped in a thin shell of exotic matter. The thought alone is unsettling, because it means that everything we thought we knew about black holes might not be what it seems. That the monsters of the cosmos may be wearing disguises. Black holes have always represented the limits of human understanding. They are the places where equations break, where the very rules of physics come undone. When you hear the phrase event horizon, you imagine a point of no return, a one-way veil where light and time are devoured forever. But for some scientists, that idea, a singularity of infinite density at the core, has always felt like a cheat. Infinity is not a solution, it is a surrender. It means that our mathematics has reached its breaking point. So ask yourself this: would the universe really allow such a thing? Would nature really create a place where the rules collapse entirely, leaving us with a riddle that cannot be solved? Or has something been hiding there all along, tricking us into believing in monsters when the truth is stranger still? For centuries, humanity has been haunted by the question, what happens when gravity wins? When a massive star burns out its nuclear fuel, it loses its fight against collapse. Its outer layers fall inward, its core caves in, and the result depends on its size. A smaller star may become a white dwarf, a corpse glowing faintly in the night. A larger one may shrink into a neutron star, a sphere so dense that a single teaspoon of its matter would weigh billions of tons. But when a star is truly massive, many times heavier than our sun, even the neutron star cannot hold. Collapse continues, unstoppable, until the star disappears from our visible universe. That is where black holes enter the picture. Albert Einstein's equations hinted at them in the early 20th century, though even he doubted they could be real. To him, they seemed like mathematical ghosts, curiosities that nature would never permit. But over time, evidence piled up. Stars were seen orbiting invisible companions. Radiation was detected streaming from unseen sources. Eventually, we even caught the first direct image of a black hole's glowing ring in 2019. Black holes, once dismissed as fiction, became fact. And yet the mystery never felt complete. At their heart lay the singularity, a place of infinite density. Physics doesn't like infinities. They are signs that our theories are broken, that something else is happening beneath the surface. That unease is what gave birth to the gravastar. Now pause for a moment and consider this. If black holes are not what we think they are, then what are we really looking at when we see one? That glowing halo captured by the Event Horizon Telescope, could it actually be hiding a gravastar instead? Could the dark monster at the heart of our Milky Way, Sagittarius A, be a cosmic trickster, fooling our telescopes with a perfect disguise? Because here's the terrifying part. From the outside, a gravastar would look exactly like a black hole. Light would bend the same way. Matter would swirl and vanish the same way. Stars would orbit as if nothing were different. And yet, inside, there would be no singularity, no death of information, no infinite abyss. Instead, there would be a hollow chamber, a bubble, filled with the same mysterious dark energy that drives the universe itself to expand faster and faster. Doesn't that sound more like science fiction than science fact? And yet this is a real theory put forward by real physicists. If gravastars exist, they don't just challenge our ideas about stars, they challenge our ideas about reality, about information, about death itself. Because black holes have always symbolized finality, the end of matter, the end of knowledge, the end of time. If gravastars are real, then maybe there is no true end. Maybe information survives. Maybe the universe is more of a trickster than a destroyer. And if that's true, then the monsters we've feared for decades are not monsters at all. They're masks, illusions, shadows hiding deeper truths. What if the most terrifying objects in the cosmos are not what they appear to be? What if black holes, those devourers of light, are really hollow shells filled with strange energy? What if everything we thought we knew about the ultimate fate of stars is a lie? Would you dare look closer? And when you do, the familiar story of a black hole begins to unravel. Every black hole starts the same way, with a star's death. A giant whose nuclear fire has run dry. Its core cools, its fuel spent, and gravity takes command. What follows is collapse, layer upon layer of stellar matter falling inward, as if the star is trying to devour itself. At first there is resistance. The pressure of atomic forces, the recoil of neutrons, even the desperate push of light trying to escape. But gravity is relentless. If the star is heavy enough, none of these defenses hold. The collapse accelerates, unstoppable, until something new is born. For much of the 20th century, scientists believed this process ended in only one way, a singularity wrapped in an event horizon. That was the script written into Einstein's equations, and it seemed to fit. The monster had a name. But then came the doubts. The singularity at the heart of the black hole wasn't a physical thing. It was a breakdown in the mathematics, an infinity, a place where equations yielded nonsense. And for physicists, that was intolerable. Nature is subtle, complex, mysterious, but it is not nonsensical. If infinity appeared, it meant the story was incomplete. So some began to ask, what if the collapse didn't finish the way we thought? What if, in those last instants, matter and energy reshaped themselves into something stranger? Something that looked like a black hole on the outside but was nothing like it within. That something was given a name in the early 2000s, the gravastar, short for gravitational vacuum star. A mouthful, yes, but in those three words lies an idea that could overturn everything we thought we knew about death by gravity. Picture it. Instead of compressing into a singularity, the star undergoes a phase transition. Just as water becomes ice under the right conditions, collapsing matter might transform into a new state. A shell, thin, dense, exotic, forms at the boundary. Inside, instead of infinite density, a bubble of vacuum energy takes shape, pressing outward. The crushing pull of gravity is balanced by this ghostly repulsion. The result? Collapse is halted, the singularity never forms, and in its place is born a gravastar, a hollow trickster dressed in the robes of a black hole. From the outside, it plays the part perfectly. Gravity bends light around it. Matter spirals inward and vanishes from view. To telescopes, to detectors, to human eyes, it is indistinguishable from the monster we thought we knew. But peel away the disguise, and you would find not a singularity, but a strange, throbbing void, a chamber of dark energy, the same force that pushes galaxies apart at the edges of the universe, a hidden heart, pulsing with the very fuel of cosmic expansion. And here lies the unsettling question. If gravastars exist, how many of the black holes we think we see are really something else? How many monsters are in truth masqueraders? What if Sagittarius A, the colossal beast at the center of our Milky Way, is not a black hole but a gravastar watching us from the shadows? If so, then the story of the universe is not one of endless destruction, but of deception, of disguises, of cosmic tricksters waiting patiently for us to notice. The story of gravastars cannot be told without the story of collapse, the violent deaths of massive stars. Because these objects, whether black hole or gravastar, are not born quietly. They emerge from chaos, from fire, from the failure of a star's most desperate struggle. So let's return to the battlefield inside a dying star. A star's life is a balance, a tug-of-war between two titanic forces. On one side, gravity pulls inward, relentless, trying to crush the star into a single point. On the other, nuclear fusion pushes outward, a furnace at the core, fusing hydrogen into helium, helium into carbon, and so on. This struggle is perfect. For billions of years, the two forces cancel each other. The sun shines steadily because its gravity is balanced by the fire in its core. Stars, for all their beauty, are really just victories in this war of balance. But victory never lasts forever. Fuel runs out. Hydrogen, the simplest and most abundant element, becomes scarce. The star tries to fuse heavier elements, climbing the periodic table, but the energy produced is less efficient. The fire weakens. Gravity, patient and eternal, begins to win. As fuel dwindles, the star swells. It bloats into a red giant, its outer layers ballooning outward, cooler and redder, while its core contracts and heats. If you were watching from afar, you'd see the star flicker and rage, shedding gas and dust into space. For smaller stars, like our Sun, this expansion ends with a whimper. The outer layers drift off into a glowing cloud, a planetary nebula, while the core becomes a white dwarf, hot, dense, but stable. But for massive stars, 10 times or more the mass of the Sun, there is no quiet ending. Their death is catastrophic. When fusion no longer produces enough outward pressure, gravity takes over. The core collapses inward in a fraction of a second. Temperatures soar to billions of degrees. In this furnace, the core crushes protons and electrons into neutrons. For an instant, the collapse halts. The neutrons pack together into a sphere just a few kilometers wide, so dense that a teaspoon of it would weigh billions of tons. This is a neutron star, one of the most extreme objects in existence. But if the star is Eve, N heavier, not even neutrons can withstand the pressure. Gravity continues its victory march. The collapse deepens, unstoppable. The outer layers rebound off the imploding core, blasting into space in one of the most violent events in the universe, a supernova explosion. For a brief moment, a single star outshines an entire galaxy. The shockwaves spread heavy elements, gold, iron, uranium, into the cosmos, seeding future stars and planets. And what remains at the center? According to traditional physics, the answer is grim, a black hole. In the black hole model, the collapse never stops. The core shrinks past all limits. Space and time bend more and more sharply until they fold in on themselves. The star disappears behind an event horizon, a boundary that nothing can cross outward. Inside, at the very heart, lies the singularity. A point of infinite density, infinite gravity, infinite curvature of space-time. Everything that falls in is crushed out of existence, erased from the universe. This is the story we've told for decades. But even as black holes became accepted, a quiet discomfort lingered, because singularities aren't just extreme, they're impossible. They mark the breakdown of our theories, and the universe, as elegant as it is ruthless, rarely tolerates impossibility. Here is where the gravastar path diverges. Imagine the collapse continuing just as before. The star runs out of fuel, the core implodes, the outer layers blast outward. But instead of forming a singularity, something else happens. The collapse slows at the very last instant. Instead of crushing everything into infinity, the star's matter undergoes a phase transition, just like water turning to ice. But this is no ordinary transformation. Instead of creating solid matter, the interior becomes filled with vacuum energy, a repulsive, outward-pushing force. This vacuum energy pushes back against her. T-gravity, halting the collapse before a singularity forms. Around it, a thin shell of ultra-dense exotic matter hardens, locking the structure in place. The result, a gravastar. To the universe outside, it looks identical to a black hole, but inside, it is radically different. Not infinite density, but equilibrium. Not erasure, but preservation. From a distance, there is no way to tell the difference. Matter falling in would vanish from sight, just as with a black hole. Light would bend, time would distort, stars would orbit, as if around an invisible monster. But there would be no singularity, no true event horizon, no absolute end. Instead, there would be a surface, Thin, exotic, nearly impossible to detect, but real, and inside, a chamber of dark energy pulsing with stability. The Gravastar is a cosmic trickster, wearing the mask of a black hole so perfectly that even our most advanced instruments cannot yet pierce the disguise. Why does this matter? Because if gravastars are real, they rewrite our understanding of the universe. They solve the information paradox by preserving information instead of erasing it. They challenge our assumptions about finality. They suggest that nature abhors infinities and prefers balance over absolute collapse. And most importantly, they may already be here. Every black hole candidate we've ever detected, from the stellar mass remnants of dead stars to the supermassive giants at the hearts of galaxies, could be gravastars in disguise. Even Sagittarius A, the dark anchor of the Milky Way, may not be what we think it is. Picture this. The Event Horizon Telescope captures its glowing image of M87, the first direct picture of a black hole. The world celebrates, headlines declare victory, and physicists marvel at Einstein's equations confirmed once again. But what if that glowing ring was not proof of a black hole at all? What if it was proof of something stranger, a gravastar, hiding behind the perfect mask of darkness? The possibility is haunting, not because it diminishes the discovery, but because it deepens the mystery. If gravastars are real, how do we find them? The answer lies in the edges, in the details too small to notice easily. When two such objects collide, the ripples in space-time may carry echoes. When matter falls against their shell, it may emit bursts of radiation, unlike anything from a black hole. Our instruments, growing sharper every year, may one day catch these differences, and if they do, the monsters we thought we knew will be unmasked as tricksters. The collapse of giants is the stage. Black holes are the familiar actors, but gravastars, if they exist, are the hidden performers, waiting just behind the curtain. We've traced the death of stars to the brink of singularity. Now we must step into the singularity itself, into the problem at the heart of black holes, the infinity that nature may not allow, because only by confronting the singularity can we understand why the gravastar matters. At the end of collapse, when the star's fire has died, when gravity has won, traditional physics tells us something extraordinary happens, the singularity, a point so dense, so extreme, that our understanding of the universe itself collapses. But let's pause here. What does that word actually mean? A singularity is not just a place, it is a breakdown, a mathematical warning sign. In Einstein's general relativity, the equations that describe gravity, space, and time behave beautifully almost everywhere. They explain orbits, the bending of light, even the expansion of the universe itself. But at the center of a black hole, those same equations explode into infinity. Density becomes infinite, gravity becomes infinite, space-time curvature becomes infinity. The human mind cannot truly imagine infinity. You can picture a large number, a million, a billion, a trillion. You can picture a galaxy of stars, each one with planets, each planet with mountains and oceans. But infinity is different. It has no boundary, no end. It is not a thing. It is an absence of limits. In physics, infinity is not a discovery. It is a failure. Ask any physicist and they will tell you infinities are red flags. They mean our theories have reached beyond their proper domain. They mean the math is no longer describing reality. And yet the black hole singularity forces us to accept infinity as real, a place where all matter is crushed into zero size, a point where time and space themselves end. It's unsettling, not just because it seems impossible, but because it feels like a story unfinished, as if the universe is saying, here your understanding ends. Beyond this point, there are no answers. But science thrives on answers. So for decades, physicists asked themselves, could this really be the truth? Could nature really allow such a breakdown? Or was the singularity a sign that our picture, it was incomplete? Part of what makes the singularity so haunting is that it is hidden behind the event horizon. This is the invisible boundary surrounding a black hole, the point of no return. Once you cross it, nothing can escape. Not particles, not signals, not even light itself. To an outside observer, the event horizon is the last thing you can see. Whatever happens beyond it is hidden forever. This is what gives black holes their mystery. From the outside, you see matter swirling, heating, glowing as it falls inward. You see jets of radiation blasting out from their edges. But what happens once the horizon is crossed? Silence. darkness, a curtain that hides the singularity, and yet physics tells us that inside that curtain lies infinity. Here is where the paradox deepens. General relativity predicts singularities, but quantum mechanics, the theory of the very small, forbids them. According to quantum physics, information about matter cannot be destroyed. Every particle, every interaction leaves a trace. But black holes, if they truly contain singularities, erase information completely. Throw in a book, a planet, a star, even a human being, and all information describing them vanishes forever. This contradiction is not small, it is one of the greatest unsolved problems in science, the black hole information paradox. Relativity and quantum mechanics, our two greatest frameworks, collide. For decades, this paradox haunted physics. Stephen Hawking argued that black holes destroy information, but others refused to accept it. The debate raged, does the universe truly erase memory, or are we missing something deeper? This is the crack where gravastars step in, because if singularities are impossible, if infinities are unacceptable, then perhaps the universe found another way. The gravastar model avoids the singularity entirely. Instead of collapsing into infinity, the star halts at the edge. Its matter transforms into something exotic, a shell of ultra-dense material. Inside, space does not collapse into a singularity. Instead, it fills with vacuum energy, a strange form of energy that pushes outward. This balance prevents the singularity from forming. The event horizon disappears. Instead of infinity, there is equilibrium. And suddenly, the paradox dissolves. Information is not destroyed, it is preserved in the shell, in the structure, in the strange bubble of vacuum energy inside. The gravastar is not just a new kind of object, it is a possible bridge between relativity and quantum mechanics. A way to reconcile the laws of the cosmos with the laws of the quantum world. But here's the unsettling part. From the outside, you cannot tell the difference. A gravastar bends light just like a black hole. It devours matter just like a black hole. It looks, acts, and behaves as if it were a black hole, which means that everything we've ever seen, every supposed black hole, could actually be a gravastar. The monster we feared may be an illusion. The singularity we dreaded may never exist. This thought is both comforting and terrifying. Comforting because it removes the infinities. Terrifying because it means we've been staring at imposters without realizing it. Let's step back for a moment. Think about what black holes mean in human imagination. They have always been the ultimate symbol of finality, the place where matter, energy, and even time itself end. If gravastars are real, that story changes. Death becomes disguise. Finality becomes illusion. The monsters we imagined turn out to be masks hiding something deeper. And that raises a haunting question. What else in the universe is not what it seems? If gravastars exist, they may already be sending us clues. When black holes merge, they release gravitational waves, ripples in space-time we can now detect with instruments like LIGO. But some scientists believe gravastars would create echoes in those waves, subtle aftershocks, faint ripples bouncing off their surfaces instead of being swallowed by an event horizon. Detect those echoes, and we would know singularities do not exist. Gravastars are real. The search is ongoing. Data is being combed for signs of these echoes. If they are found, it would rewrite astrophysics forever. Why does this matter to us? Tiny beings on a pale blue dot circling an ordinary star. Because gravastars remind us of something profound, that the universe may not be the brutal destroyer we think it is. That memory may not vanish. That information, once written into the cosmos, survives in some form. This speaks not just to physics, but to philosophy, to meaning itself. If nothing is ever truly lost, if the universe preserves information even in its darkest corners, then perhaps destruction is never as final as it seems. And in that, gravastars are not just scientific objects, they are metaphors for hope, for continuity, for mystery preserved. So here we are, staring at the singularity, the supposed abyss of infinity. For decades, it has haunted physics, the place where our understanding stops. But the gravastar theory offers a different vision, a way for the universe to continue without collapse. It tells us that maybe, just maybe, the monsters at the heart of galaxies are not monsters at all. They are masks, tricksters, shadows hiding deeper truths. We've confronted the singularity problem. We've seen how gravastars may avoid infinity, preserve information, and reconcile the laws of physics. But how exactly did this idea emerge? Who dared to challenge the might of black holes and propose this radical alternative? To understand the birth of gravastars, we need to step into the early 2000s, into the minds of two physicists bold enough to question the most terrifying objects in the cosmos. At the heart of physics lies a simple rule: information cannot be destroyed. This is not information in the everyday sense, not books, not data, not memories, but the quantum information carried by particles themselves. Every particle, every state, every interaction leaves behind a trace. The universe is a ledger that never forgets. But black holes break that rule. Stephen Hawking, one of the greatest minds of the 20th century, was among the first to expose the paradox. In the 1970s, he showed that black holes are not completely black. Through quantum effects at their edges, they radiate energy, what is now called Hawking radiation. This radiation is random, featureless, and as the black hole emits it, it slowly shrinks. Over unimaginable spans of time, it evaporates completely. But here's the catch. The radiation contains no record of what fell in. The book you threw into the black hole, the star it consumed, the planet it devoured, all that information is gone. The black hole evaporates into featureless heat, leaving no trace of what was lost. This violates the deepest law of quantum mechanics. It is as if the universe itself develops amnesia. You might ask, why care? If a black hole erases information, why does that matter to us, tiny creatures far from their reach? Because physics is built on consistency. If information can be destroyed, then the foundations of quantum theory crumble. And if quantum mechanics fails, everything else fails, from the chemistry of life to the structure of matter. The paradox is not just about black holes, it is about whether the universe itself makes sense. This is where gravastars shine. Unlike black holes, gravastars have no singularity, no event horizon, no final erasure. Instead, they have a shell, a boundary where information might be preserved. When matter falls onto a gravastar, its details are not lost forever. They may be encoded in the exotic shell, stored in the vacuum energy within, or reflected in ways we do not yet understand. In this way, gravastars sidestep the paradox entirely. They allow relativity's predictions of collapse and gravity's power, but without breaking quantum law. They preserve the ledger of the universe. To understand how profound this is, remember that physics is divided into two great pillars: general relativity, which governs the very large, planets, stars, galaxies, the curvature of space-time; quantum mechanics, which governs the very small, atoms, particles, the strange world of uncertainty. These two frameworks work beautifully in their own domains, but put them together, as in the heart of a black hole, and they clash. Relativity predicts infinities. Quantum mechanics forbids them. The gravastar, in its strange equilibrium of vacuum energy and exotic matter, may be the bridge, a structure where both theories coexist without contradiction. Imagine for a moment that every action, every event in the universe is written in a cosmic ledger. A photon bounces off a rock, recorded. A star burns its fuel, recorded. You lift your hand, recorded. Black holes, in the traditional view, are pages torn from that ledger. Once something crosses the event horizon, its entry is erased. The story is incomplete. But gravastars suggest a different ending. The ledger remains intact. The story continues, even if hidden from our view. The universe in this picture never forgets. Stephen Hawking himself wrestled with the paradox until the end of his life. At first, he insisted information was destroyed. Later, he softened his stance, hinting that perhaps information could escape after all. The gravastar was never Hawking's invention, but it sits squarely in the space he carved out, the search for a resolution to the paradox. It is one of several ideas competing to restore balance between relativity and quantum mechanics, but it remains one of the most elegant. Think of the implications if black holes truly destroyed information. It would mean that reality is not deterministic, that events could vanish without a trace, that the universe itself could break its own rules. For science, that would be chaos. For philosophy, it would be terror. Imagine a reality where memory itself can vanish, where the story of existence is not just hidden, but deleted. Gravastars, by preserving information, return order. They restore continuity. They make the universe consistent again. But here is the haunting twist. Gravastars achieve this while pretending to be black holes. From a distance, the disguise is perfect. Matter vanishes from view, light bends into rings, stars orbit unseen centers. To us, it looks like erasure, but inside, the ledger is safe. The gravastar is not a destroyer, but a vault, a cosmic safe, where information is locked away rather than burned. If gravastars preserve information, how can we prove it? The answer may lie in their radiation. Black holes emit Hawking radiation, pure, featureless heat. Gravastars, by contrast, might emit radiation with subtle imprints of the information stored within, tiny variations, echoes, fingerprints. Future detectors may one day capture these differences, and if they do, we will know the paradox is solved, not by black holes, but by gravastars hiding in plain sight. There is something deeply human about his debate. We are creatures obsessed with memory, with record, with legacy. To be forgotten is a kind of death, to be erased is the ultimate horror. Black holes in their traditional form are erasers. They represent the fear that nothing lasts, that memory itself can vanish. Gravastars, by contrast, whisper a different story, that even in collapse, even in death, something is preserved, that the universe itself remembers. This is why gravastars are more than just exotic physics. They are metaphors, they are bridges. They tell us that the extremes of nature, gravity and quantum mechanics, need not be enemies. They can coexist, balanced in the hollow shell of a gravastar. And if the universe can reconcile such extremes, perhaps we can too. The information paradox is not just a puzzle, it is a mirror held up to reality. Do we live in a universe that forgets or one that remembers? Do stars end in erasure or in preservation? Gravastars offer an answer, but answers are not enough. To prove their existence, we must learn to see through their disguise, to search for clues hidden in light, in gravity, in echoes that ripple across space-time. From the beginning, gravastars have lived in disguise. Outwardly identical to black holes, they leave us with an almost impossible challenge. How do you find a trickster hiding in the skin of a monster? To unmask a gravastar, we must learn to see the tiniest differences, the faintest echoes, the subtlest fingerprints left on the canvas of space-time. Here's the problem. From the outside, a gravastar bends light exactly like a black hole. It pulls stars into orbits the same way. It distorts time and space just as brutally. Our telescopes see the glow of matter spiraling inward, the violent accretion disks, the relativistic jets shooting into space. But whether the dark center is a black hole or a gravastar, the performance is identical. It's like watching a play where two actors share the same costume, same mask, same lines. How do you tell them apart? The answer lies in the details. When matter falls toward a black hole, it forms a disk of swirling gas. Friction heats this disk to millions of degrees. It glows in X-rays, sometimes brighter than entire galaxies. But once the matter crosses the event horizon, it is gone forever. No reflection, no return. A gravastar, though, has no event horizon. Instead, it has a shell. And when matter slams into this shell, something different happens. Instead of disappearing completely, some of the energy might be released in bursts, subtle differences in timing, brightness, or spectrum. If we look closely enough, those differences might betray the imposter. Perhaps the most promising clue comes from gravitational waves, ripples in space-time itself. When two black holes collide, the universe trembles. Waves ripple outward at the speed of light, carrying the story of the merger across billions of light years. Detectors like LIGO and Virgo have already recorded these cosmic songs. In a black hole merger, the waves fade smoothly as the new black hole settles. But if gravastars merge, something stranger may happen. The waves could echo, faint reflections bouncing off their surfaces, delayed whispers following the main event. Scientists have searched for these echoes in gravitational wave data. Some claim to see hints, others argue the evidence is weak, but the possibility is electrifying. If echoes are confirmed, it would be the first fingerprint of a gravastar. Another arena for clues is in the jets of energy that black holes produce. Some black holes, especially supermassive ones, power quasars, cosmic beacons so bright they outshine galaxies. These jets come from matter just outside the event horizon, accelerated to near light speed. But if a gravastar has a surface instead of a horizon, the dynamics could change. The timing, intensity, or shape of these jets might differ, however, slightly. Astronomers are combing quasar data, searching for anomalies, patterns that don't quite fit the black hole model. Could some of those oddities be gravastars masquerading as monsters? In 2019, humanity celebrated the first direct image of a black hole, the glowing ring of M87. In 2022, we saw Sagittarius A, the dark heart of our own galaxy. But what did we actually see? Not the black hole itself, but its shadow, light bent around its edge. A gravastar could create the same shadow. To tell the difference, we would need sharper images, more resolution, finer detail. The Event Horizon Telescope and its successors are being pushed to their limits, hunting for tiny discrepancies in the glow. The challenge is immense, but so is the reward. If the shadow flickers differently, if the brightness shifts in ways unexplained by black hole theory, the mask could slip. The problem with hunting gravastars is not lack of ideas, but lack of precision. Our instruments are still young. LIGO detects space-time ripples smaller than a proton, yet even that may not be enough. The Event Horizon Telescope links radio dishes across the world, yet its vision is still blurred by cosmic dust. We are like detectives with smudged fingerprints trying to solve a case where the suspect wears a perfect disguise. And yet, science advances. Each new telescope, each new detector sharpens our vision. The hunt is only beginning. Some scientists have even suggested stranger tests. Thermal signatures. If matter piles on a gravastar's shell, it could heat differently than around a black hole. Neutrino emissions. Exotic particles might escape from gravastars in ways they never could from true black holes. Gravitational ringing. After mergers, gravastars might vibrate differently, leaving subtle imprints in space-time. None of these are confirmed, all are speculative, but each represents a thread to pull, a shadow to chase. Why go to such lengths to find gravastars? Why chase whispers and shadows? Because the stakes are nothing less than the foundations of physics. If gravastars are real, they solve the information paradox, they reconcile relativity with quantum mechanics, they reveal that singularities are illusions. They would show us that the universe is cleverer than we imagined. Not a brute eraser of memory, but a trickster preserving secrets behind a mask. There is something profoundly human about this hunt. We have always been drawn to mysteries hidden in plain sight, to myths of gods in disguise, demons lurking behind masks, tricksters playing roles. The gravastar is the scientific version of that myth. It wears the costume of a black hole, performing the same role, but hiding another identity. And like all tricksters, it dares us to look closer, to question the obvious. The next decades will be decisive. New gravitational wave observatories like LISA, Laser Interferometer Space Antenna, will listen from space, more sensitive than ever. Future expansions of the Event Horizon Telescope may sharpen its vision, revealing details hidden in the shadows. Particle detectors may catch exotic emissions that betray a surface where none should exist. Each of these tools is a key, and behind the locked door may lie the truth, the gravastar, the shadow that hides within the shadow. But even as we search, we must ask, what if we never find them? What if gravastars remain perfect disguises, indistinguishable from black holes? Then the paradox remains. The singularity haunts us. The ledger of the universe remains in question. And perhaps that is the gravastar's greatest trick, not to reveal itself, but to keep us searching, questioning, never satisfied. The hunt for gravastars is the hunt for truth itself, for answers to paradoxes, for clarity in shadows. But whether or not we find them, their possibility already changes us. Because gravastars remind us that the universe may despise finality, that endings may be illusions, that even in the heart of darkness there may be secrets preserved. And this takes us to the next step, not the science of observation, but the philosophical tremors gravastars unleash. If the monsters of the cosmos are illusions, what does that say about reality itself? The gravastar is not just a scientific proposal, it is a philosophical earthquake. Because if gravastars are real, then black holes, the monsters of science fiction, the symbols of finality, the cosmic graves, are illusions, masks, tricksters, and what they reveal about the universe may shake not only physics, but our deepest assumptions about reality itself. For as long as we've known them, black holes have stood for endings, the point of no return, the place where matter, energy, and even time itself vanish without trace. To poets and scientists alike, they were the ultimate metaphor, death made cosmic. But gravastars whisper something else. They suggest that endings may not exist, that what we thought was annihilation is really transformation, that the universe may prefer continuity to finality. If that is true, then the singularity, that the abyss of infinity, was never real. It was our misunderstanding. Nature is not erasing, it is hiding, preserving. This thought sends tremors through philosophy because it means that reality itself may be layered with illusions. The black hole was not the final word, but a mask for something stranger. How many other cosmic truths might be disguises? How many other infinities might be illusions? The gravastar becomes more than an object. It becomes a parable, a reminder that what we see is not always what is. If gravastars preserve information, they echo something deeply human. Our obsession with memory, with legacy, with the fear of being forgotten. Black holes terrified us not only because they destroy matter, but because they erase memory. They represent the ultimate oblivion. But gravastars say, nothing is forgotten. Information survives. The universe remembers. And in that story, we glimpse hope. The cosmos is not cruel erasure, but strange preservation. Not death, but disguise. Across cultures, myths speak of tricksters. Lo, Ki, Coyote, Hermes, Anansi, beings who deceive, disguise, play roles to reveal deeper truths. The gravastar is the trickster of astrophysics. It wears the mask of a black hole, plays the role of the monster, but hides a different identity. In tricking us, it forces us to look closer, to question deeper, to see beyond appearances. It is as if the universe itself is playing the role of the trickster, luring us with darkness only to whisper, there is more than you think. Consider what this means for science itself. For decades, black holes were dismissed as fantasies. Then they became accepted fact. Now gravastars suggest they may not be what we thought at all. Knowledge is fragile, certainty is temporary. The truths we proclaim today may be masks hiding tomorrow's revelations. This is not a weakness, it is the essence of science and the willingness to question, to doubt, to chase shadows. Yet there is also fear here, because if nothing is ever erased, if the universe remembers everything, then what of us? What of our mistakes, our cruelties, our wars, our forgotten histories? The gravastar forces us to ask, do we want a universe that remembers, or one that allows erasure? Oblivion, terrible as it is, offers mercy. Continuity, comforting as it seems, offers judgment. The ledger cannot be wiped clean. In that sense, gravastars are not just cosmic tricksters. They are cosmic mirrors, reflecting back our own unease with memory and meaning. If black holes are illusions, then even death itself becomes suspect. We've always thought of death as finality, as the singularity of life. But gravastars hint at a universe where nothing is final, where even endings are transformations, not erasures. What does that mean for us? Are we two masks, tricksters, continuities hiding behind the illusion of finality? The philosophical tremor deepens. Gravastars don't just challenge astrophysics, they challenge our understanding of existence. Step back and consider the larger pattern. At every turn, the universe surprises us. We thought the Earth was the center. It was not. We thought the stars were eternal. They die. We thought the universe was slowing. It accelerates. We thought black holes were final. They may not be. The universe hides, disguises, deceives. It plays roles to draw us deeper into its mysteries. Perhaps the universe itself is the trickster, and gravastars are just one of its masks. For us, staring into the night sky, gravastars echo our own uncertainty. We too wear masks. We too hide truths beneath appearances. We too struggle with endings that may not be endings. The cosmos, in its vastness, reflects our own fears and hopes. Gravastars are cosmic tricksters, but they are also metaphors for us. So when we speak of gravastars, we are not only speaking of exotic shells and vacuum energy, we are speaking of philosophy, of myth, of the fragility of truth. They remind us that endings may be illusions, that destruction may be disguise, that even in the heart of darkness, memory survives. The tremor they unleash is not only scientific, but existential. They shake the ground beneath our assumptions, leaving us with awe, unease, and wonder. The Gravastar is a scientific proposal, yes, but it is also a parable, a whisper that the universe may be stranger, kinder, or crueler than we imagine. We have said their birth, their disguise, their paradox, and their hunt. We have felt the philosophical tremors they unleash. Now comes the final step, resolution. If gravastars are real, what do they mean for the universe's story? For galaxies, for time, for us? The Gravastar began as a question, a whisper in physics, a challenge to the monsters we thought we understood. And now, as we arrive at the end of our journey, we see what it really is. Not just an exotic object in the cosmos, but a symbol of how science works, how reality hides, how mystery endures. Black holes themselves were once speculation, a strange prediction from Einstein's equations that even he doubted could be real. For decades, they were dismissed as curiosities, mathematical oddities. And yet, today we not only believe in them, we have imaged them. We have watched stars orbit invisible centers. We have heard their collisions ripple across space-time. Black holes went from fantasy to fact. Could gravastars follow the same path? Could the tricksters we imagine today become tomorrow's discoveries? The line between speculation and discovery is thin. Gravastars live right on that edge. If gravastars exist, they could be the anchors of galaxies, the engines of quasars, the hearts of cosmic structures. They would not just be curiosities, but key players in the universe's story. Every galaxy we see, every swirl of stars, every cosmic dance, perhaps driven not by monsters but by tricksters. It is possible that the Milky Way itself, our home, is built around a gravastar, Sagittarius A. The dark presence at the center could be no black hole at all, but a hollow bubble of vacuum energy hidden behind a perfect mask. If true, then we orbit not around a destroyer, but around a cosmic vault. At the core of the gravastar theory lies the question of information. Does the universe forget, or does it remember? Black holes seem to erase. Gravastars suggest preservation. If they are real, then the ledger of the cosmos remains intact. Every star, every particle, every interaction is remembered, written into the strange fabric of vacuum energy and exotic matter. In that sea, gravastars are not graves, they are archives. The universe itself becomes a library, storing everything that ever was. There is something deeply elegant about a universe without infinities. Singularities were always unsatisfying, always suspicious. They marked the breakdown of our theories, the edges of our maps. Gravastars remove those infinities. They show us that nature prefers balance over collapse, structure over chaos. And in doing so, they give us a universe that is consistent, continuous, whole. But perhaps the most haunting lesson of gravastars is not scientific, but mythological. They remind us that the universe wears masks, that reality is layered with illusions, that what we think we know may be disguise. Black holes were monsters, gravastars may be tricksters, and who knows what masks lie beyond them. The universe itself may be the greatest trickster of all, luring us with shadows, challenging us with paradoxes, forcing us to look deeper. The hunt is not over. Future gravitational wave detectors may find the echoes that betray gravastars. Sharper telescopes may reveal details hidden in the shadows. Theoretical physicists may refine the models, showing us how exotic shells and vacuum energy truly behave. In the years to come, we may confirm their existence, or we may find something stranger still. But either way, the gravastar has already done its work. It has shaken us, challenged us, reminded us that certainty is temporary and mystery eternal. Why do we chase these questions? Why spend lifetimes searching for objects we may never touch, never see directly, never truly know? Because in chasing them, we learn not just about the universe, but about ourselves. We learn that endings may not be endings, that memory may survive, that the monsters we fear may be illusions, and perhaps deep down we hope that the same is true for us, that we too are not erased, that we too are preserved in some form, some memory, some strange archive written into the fabric of reality. So what are gravastars? Exotic shells filled with vacuum energy, solutions to paradoxes, tricksters wearing masks. They are all of these and more. They are symbols of the universe's refusal to be simple, proof that reality always holds another layer, another secret, another disguise. Black holes taught us to fear finality. Gravastars teach us to question it, and that is their greatest secret. Not that they exist, but that they remind us to never stop looking, never stop doubting, never stop chasing the shadows that hide deeper truths. In the end, whether gravastars are real or not almost doesn't matter, because they have already expanded our imagination. They have already forced us to think beyond the singularity, beyond infinity, beyond finality. The universe is vast, dark, and strange, and gravastars are proof that we have only just begun to scratch its surface. They are whispers from the cosmos, hinting that the darkest monsters may be illusions, that the deepest graves may be archives, that the universe is not what it seems. And so the story does not end. It continues, as all stories do, into deeper shadows, stranger truths, secrets yet to emerge.